Thank you. So we're talking about linear stability of a dynamical system, one-dimensional. So we have our mx dot dot is some f of x, and in terms of an energy, that's minus some v prime potential energy. And we have an equilibrium point. If f at that point is 0. And we're thinking about forces only depending on x, which remember we call conservative. Okay, so the idea is I want to know if I start close to that point, how does the system behave? And so what we do is we take x, say close to xe, and ended last time by saying the idea is to Taylor expand that Newton's second law. And so the idea is I write f of x is approximately f of xe plus f prime of xe times x minus xe plus, okay, it's infinite, but we can sort of smush all the rest of the terms into I don't know if you've seen that notation before, but that's called the big O, and that just says that everything else is x minus xe squared or smaller. I'm taking x close to xe, so that term is smaller than that one, and x minus xe cubed is smaller than that, and so on. Okay. So hope that Taylor series should be familiar. Just another way to kind of rewrite that. If I let so this is psi of t. I'm going to define that as the difference between x, to remind ourselves is x of t, minus xe, which is not a function of t, just a constant. Then that equation becomes f of x, which is xe plus psi, is approximately f of xe plus f prime of xe times psi, plus things that are smaller than or equal to the same size as psi squared. So that ends up being a more useful representation. Hopefully you see that that's exactly the same Taylor series, just sort of shifting the way I'm writing it. This ends up being a slightly more useful representation because what I want to do is I want to take Newton's second law and I want to insert x of t is xe plus some psi. And I don't know what that psi is. That's what I'm trying to work out. And so what I get is if I take two derivatives, that just goes to the psi. So I get m times the second derivative of psi is f of xe, which is 0 by construction. So it's f of x, which is xe plus psi. I get f of xe, which is 0, plus f prime of xe times psi. Plus, is the other notation you'll sometimes see, dot, 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 means all the rest of the terms in the Taylor series which are smaller than the terms I'm keeping. So I'm supposing by construction that psi is small, because I'm looking at the behavior very close to the critical point, the equilibrium point. So by assumption, psi is small, which means all this stuff in dot, dot, dot is smaller than the stuff that I've kept there. Okay? So, therefore, this gives an approximation to the behavior or the motion close to near xe. So in fact, what we'll do is we'll go even further and we'll just think about that equation. So I'm going to completely get rid of the dot, dot, dots, keeping in mind that they're still there. So what I'm solving, I'm going to think about that equation, and I'm going to say that equation dictates the behavior of the system near the equilibrium point, keeping in mind that that's an approximation because there's a whole lot of dot, dot, dot that I'm throwing out. Okay? And note that that's the same as the equation m psi dot dot is f prime, and f prime is minus v double prime. Ooh, running out of space on the board. Sneak a psi in there. And this is quite telling because we were playing these games of energy landscapes last time. And in the energy landscape point of view, if I plot V as a function of x, whatever shape it might have, we have this view of a ball rolling in a valley. And in that sense, it's quite intuitive that the equilibrium points are the flat bits, which are the bottom of the valleys or the top of the hills. And that is what we get there. That's where V prime is 0 or F is 0. And their stability, intuitively, we kind of understand that that seems stable. If I nudge the ball, it stays close. And if I nudge the ball, it goes away. And that's going to be what we see from looking at that equation, because it really comes down to two cases. Well, 2.5 maybe cases. So case 1 is it's the sign of this term f prime of xe. So if f prime xe is positive, sorry, let's start the other way, negative, or equivalently, v double prime positive, so there's the minus there. What I'm really asking is what kind of function is this psi of t? And if it doesn't already like immediately pop into your head, train yourself so that it does. When you see this equation, y double prime plus k squared y equals 0, I want that to immediately pop into your head, sines and cosines. And when you see y double prime minus k squared y equals 0, that should immediately pop into your head, exponentials. And that's everything, because that's what we have. We have m psi dot dot, put the f prime on the other side, and either psi is going to be exponentials or sines and cosines. And sines and cosines is what we call stable, because those are functions that stay bounded, and exponentials, but there's one exponential that goes off and gets big, and that's what we're going to call unstable. And it's entirely coming from that, the sign of f prime. So in this case where f prime is negative, I put it on the left-hand side and it's a positive, and that's sines and cosines. So in particular, if f prime is negative, I can write psi of t is some constant times a cosine of omega t plus another constant. That's the trick we did the other day, where that omega is defined as f prime, the square root of f prime xe over m, and I think I need a minus sign, defines a frequency, and this is what we call a stable equilibrium. Now, what we strictly mean is that if the system starts near to the equilibrium, it stays near. And the other case, of course, is just the opposite. So if f prime xe is positive, that means I have a positive times a psi on the right, which is a negative on the left, which is that case. Psi is exponentials. And let's also note that that's the equivalent to v double prime xe being negative. Then psi is exponentials, which we can write as an e to the pt plus b e to the minus pt, where here p, I'm not going to use omega because omega looks like a frequency. P has the same kind of definition, a square root f prime at xe over m. And this is what we call an unstable equilibrium. Now, of course, there's a positive exponential and there's a negative exponential, and you might say, okay, well, that one's decaying, so I stay close. But the presence of that one means it's unstable, because what I mean by stable is that any initial conditions that start close must stay there. So even though it might be possible to get rid of that a, this is still an unstable because of the positive exponential there. And, well, a couple of comments. So on the one hand, that exactly matches our intuition here. So if I'm looking at the energy landscape, it's the second derivative of V. The first derivative of V tells us where our equilibria are, the hills and the valleys. The second derivative tells us whether it's stable, V double prime, negative or positive. I'm either at the bottom of a valley or the top of a hill. Right? To be a little bit careful, again, this is the behavior. I've started at my equilibrium point and I've moved a little bit from it. And I'm asking, if I then let that go through the dynamics, what does that function look like? This is only how it looks sort of initially. This is only valid as long as I'm ignoring the dots. So it's not saying that this is exactly what the particle does, but it says that the particle goes away because there's an exponential. And once it goes away, this is no longer valid because now psi is no longer small and I need to include other terms or go back to the full system. Okay, so let's just make a note. This analysis is only valid if psi remains small. So our solution loses validity if psi, or you might say the magnitude of psi, is not small. Okay. There's a sort of third scenario, which is that what happens if f prime itself is 0 as well? And the short story is that this is a messier case to worry about. And for the most part, we won't worry about it. But these arguments don't work anymore because that psi term just isn't there. So it means I have to go to higher terms in my Taylor expansion. And I think it's safe to say that it's a case that we won't really think about, but just to give you something as a simple example, compare Um, want it that way, minus x cubed. You put a minus here and a minus there. So think about that system, forget about where it's coming from, just as an equation. My force minus x squared, and my force is a minus x cubed. X equals 0 is an equilibrium point. You don't really have to do a Taylor expansion. It's already expanded for you around 0. It's just a square and a cube. So that's f prime at 0 is 0 in both cases. And indeed, f double prime 0 in one of them. Right? What's going on in these two? A nice way to think of it is just to think about the energy diagram, energy landscape. So here, V is a x cubed over 3. Right? And there V is an x to the 4th. So what do you anticipate stable and unstable? So that's x cubed, and that's x4, and we're talking about the stability of that point right there. And it's pretty clear that that looks very stable. Indeed, it is. If you were to solve this, you can't get it nice and analytically, but we can certainly reason that that's stable and this is unstable, even though it looks almost half stable if I go that way. If you nudge this ball that way, it would eventually then start rolling back this way and plunges off. In fact, this is an example where it goes off to infinity in finite time, if you were to analyze that one. So this is indeed unstable. X equals 0 is unstable, and here x equals 0 is stable. But we can't do it nice and analytically. Okay? All right, so I want to use these tools, and I want to work through a more complicated example than the ones we've been thinking about. So in fact, this is from long past exam, 2003. It's still kind of a nice relevant question. The idea is the following picture. I have a little block there, and I have a spring, and what I imagine is so let's call this distance d, and what I'm going to do is I'm going to attach a mass to the x-axis, and then I'm going to attach the mass to that point by a spring. Okay. And let's call this distance x of t. And then what we'll suppose is that that spring, so we'll have a mass m, attached to, actually let's say it this way. A mass m slides along I want to use more or less the language that was used in the exam so we can analyze some of the key words. Slides smoothly along a horizontal wire and is attached to the point 0d by a spring of length, and length means rest length, L, where L is greater than D, actually, let's not make that assumption right away. Let L be generic at the moment. By a spring of length L and spring constant K. Okay. What we want to do is get a Newton's second equation for that motion and analyze any equilibria and their stability. So, this is more complicated. This is 1D motion because that particle is stuck on the x-axis. So it's only allowed to move in the x direction. But of course, my force is kind of not living in that axis. So there's a little complication to make sense of. And intuitively, it's nice to imagine this experiment. So if L is less than D, you kind of imagine that just to be at x equals 0, the string has to be stretched, and it would just be very happy to stay right there. Where it gets interesting is if L is greater than D, because now the spring wants to be away from x equals 0. Okay? Spring is getting compressed. Okay, so this is a ramp up from the springs we've been thinking about, so let's take it carefully. I need to think about Newton's second law. And even though it looks like 1D motion, let's be safe. Newton's second law is a vector equation. And what I want to do is I want to account for the forces and, of course, the motion. So the motion, the position of the particle is just r of t is x of t I. There's no position in the y direction. The spring force so what do we know? So springs, we've said spring is a force that points along the direction of the spring. And it's equal to a spring constant. The magnitude is a constant times how much the spring has been stretched, right? So what I need to do is think about that direction right there, because that's the direction the spring is actually pointing. And if I call that direction vector tau, then what I can do is say F as a vector is spring constant times the change in length of the spring. The spring wants to be length little l, but what is the actual length of the spring? Well, I just look at the triangle, and it's the hypotenuse of that triangle, which is square root of x squared plus d squared. So it's square root x squared plus d squared minus l, and it's pointing in the direction of tau. Now let's think about, do I have that sign right? So if root x squared minus d squared is greater than L, I've drawn tau pointing that way, then the spring force is pulling on the mass that way. So that's correct. Okay, but what is tau? Well, tau, I need to do some geometry, and one thing I can do is I can make this angle, give that a name, call that theta. And if I call that theta, then I see that tau is, careful there, so it's got a sine theta in the j and a minus cosine theta in the I. J being the y axis. Okay, so therefore, if I write down Newton's second law, I get m times x dot dot I equals this kind of ugly thing with the square root, and it's got the tau, these two components of the tau, so that's k minus cosine theta I plus sine theta j. And now I look at that equation and I claim I must be missing something. What am I missing? Or why must I be missing something? There's only an I on the left side, and there's some forces. There's one force over on the right side, and there's nothing balancing it. In fact, you could solve this problem without even thinking about that, but it's not quite right the way we've written it. What am I actually missing? So there's something here in the wordings. M slides smoothly along the horizontal wire. And we'll see that wording a lot because this is kind of a nice sort of setup of a problem. Smoothly means there's no friction. The wire is not resisting itself, the particle, to move along the wire. So that means the wire can provide a force to the particle itself, but if the wire is providing a force, that force is not along the length of the wire is nice and smooth. But the wire can also apply a force to the particle in the transverse direction, the perpendicular direction, and that's what we've been calling a normal force. And there must be a normal force because that equation doesn't balance in the j the way I have it. So we can just do it this way, plus nj. And you can think of it, because I've constrained that particle to be on that wire, the string is trying to pull, right? The spring is trying to pull the particle off the wire, and the wire is applying a force that exactly balances that. In other words, we can work out n just from looking at the j component there. We don't need it for solving the problem, but it is there. So that's our reaction, normal reaction. Okay, so I have, if I then look at just the I component of this equation, I have something I can write down for x. It's not very nice. We can go one step further by observing that if I look at that triangle again, cosine theta is x over the square root of d squared plus x squared. So therefore, I can stick that in here, and I've got a root x squared plus d squared there, which is going to multiply. That looks all right. This doesn't look as nice because it's just minus an L multiplying that. But if I'm just going to put a couple of algebraic steps hidden here. It's not too hard. If you shuffle things around there, you get the following. X dot dot is k over m. So I'm going to bring the m to the left side. K over m times x times L over root d squared plus x squared minus 1. I think you can see I've taken that times that, and then I've canceled out the square root from the denominator there. Pick up an extra x here. Okay, now it at least looks like the kind of equation we've been analyzing, so let's call that thing f of x. And now we can start to, well, that's a complicated equation. I have no hope of just solving that thing with the square root living in the denominator, but I can analyze equilibria. So we start by saying equilibrium points are where f is 0. So f of x equals 0. And, okay, there's one clear solution at x equals 0. And there's a second solution where the square root of d squared plus x squared equals L, so that the minus 1 goes away. Right? So I can square that, subtract square root. That's a second equilibrium, and I'm just going to leave it as the solution of that for now. And you see there's a plus or minus there because there's a sort of left-right symmetry to the problem. The spring can go the point can go left or right, and it looks the same. Right, so now I want to ask about equilibrium stability. So for stability, we play the game we've been playing over here. And, well, just write what we've already written. If I take x to be x equilibrium plus psi of t, we already know generically that psi dot dot is equal or approximately equal to f prime xe times psi. Conceptually, there's nothing hard here. I just take that f, I take a derivative, I evaluate it at one of those 2 points, and ask whether it's positive or negative. Practically, it's not very nice because the derivative is quite messy, and that point is hidden inside, that xe is hidden inside a square root in a not very nice way. So, nevertheless, one thing, yeah, we're a little bit careful with our algebra. We can keep these calculations from getting too messy. So f prime has a k over m times this L over root d squared plus x squared minus 1. And then if I take the derivative of the second term, I've got an x squared to the minus 1/2. So that becomes a minus k L x squared. So I pick up an extra factor of x, which has that x there, and that becomes over d squared plus x squared to the 3/2. So let's take 2 scenarios. One, xe equals 0. F prime of 0 is easy enough to do here. That one drops out. This is just that constant. So it's just k over m L over root, sorry, it just becomes L over D minus 1. X goes away there. And what are we asking? We are asking whether that is positive or negative. And you can see something changes based on L and D. Right? So imagine I fix D, and then I'm changing the length of my spring. So what we've said over here, stable if f prime is negative. So this is stable. Is stable. This is going to be negative if L is less than D. So the L over D minus 1 is negative. And unstable if L is greater than D. With some sort of transition happening at L exactly equal to D, but the L equals D case falls into case 3, which we won't worry about. The other equilibrium points, potentially things get very messy. So x, E is by definition plus or minus L squared minus D squared to the 1/2. And the first observation is that that equilibrium doesn't exist unless L is greater than D. And if L is less than D, this is complex. That doesn't physically exist. So this only exists if L is greater than D. And if L is greater than D, in which case f dash at that point well, one shortcut you can work out is that that equilibrium came from setting that whole thing equal to 0. Right? That's where I got that equilibrium, was that thing equal to 0. And now that same term is showing up again here. So I can save myself some algebra by observing that at that xe, that bit is by construction 0, which means the stability is going to be guided by whatever is happening over there. Right? And in fact, I can save myself some algebra on the entirely. What can we say about stability? Does anyone see the shortcut? Yeah. It's an x squared and a squared to the 3/2. So that term, ignoring the minus, is positive for any xe that exists. And the minus means that it's negative. So despite the ugly looking potential algebra, if we step back, we realize we don't have to do any algebra at all, in which case f prime is negative, and f prime negative means stable. Okay. So let's kind of make sense of this as a thought experiment, and a nice way to do that is to draw what's called a bifurcation diagram. And the idea of the bifurcation diagram is you plot the equilibrium point as a function of a tuning variable. I'm imagining a thought experiment. In my experiment, I'm changing the length of the spring. So I'm going to make this axis the length of the spring. And as I change L, I get these different equilibrium points, and I want to draw them as curves. So one of them, and of course we know there's, actually I'll do it because I've done it here. I'll do it slightly different. I'll call that D. Same thing. I keep my spring, and I change the distance that the spring is from the wire. Okay? So of course something happens at D equals L. When D is greater than L, less than D, I only have one equilibrium. So up here, this axis is like xe. Okay? I only have one equilibrium, and it's xe equals 0. And what we do in a diagram like this is we use a solid line to indicate that that solution equilibrium is stable. And we'll use a dashed line to indicate unstable. When D becomes less than L greater than D, that equilibrium is still there, but it becomes unstable. So that's what I've just drawn is case 1, x equals 0, and it's always there, x equals 0, but its stability changed. And then I have this other solution, which is root L squared minus D squared, which looks like a sort of inverted parabola in this diagram that only exists in the case D less than L. So it's sort of like this, and that's the plus or minus. So that's exactly that pair of curves there. And I've drawn it as a solid line because that branch is stable when it exists, but it only exists for D less than L. Okay, so take some practice looking at this diagram, but you can actually read off what would happen in this experiment. So I've got my spring. Suppose the spring is vertical, and I've got it at D. I'm out here. And I just start pushing down, right? I start bringing the spring, the D point closer to the wire. So once it gets to the rest length, what happens? So we're not actually solving the dynamics, right? We're just seeing what happens to equilibria. So that point where it was vertical becomes unstable, and suddenly it wants to shoot either to the right or to the left because the spring is becoming compressed, and so it gets pushed out one way or the other symmetrically to one of these branches, and the further I push it down, the more it wants to push out that way. Okay? So that's the idea of a bifurcation diagram. I'll give you an exercise to play with that in the problem sheet as well. Another note I want to make. So you'll be tempted, some of you will be tempted to just memorize what I've put over here, and given any problem you say, okay, I just need the f, and I just need to evaluate f prime at the equilibrium point and look at its sign. And in this problem, you would have, if you just kind of done that blindly, you would have kind of gotten down a road of very ugly algebra. We managed to kind of avoid the ugly algebra by thinking carefully about what terms are there. It's also worth noting that we don't only have to think about the sign of f prime of xe. So f prime xe sign is not the only way to determine stability. Doing here. Right, f prime is not the only way to determine stability. The general principle is what is the behavior of this function psi of t. So we sort of saw it there. Just to give you a different example, let's consider this is a completely made up problem. X dot dot equals x squared e to the 2x cosine x. Okay, that's a messy right-hand side. Now let's suppose we want to know the stability of x equals pi over 2. So pi over 2 is an equilibrium point because cosine is 0, right? And if I want to call that f and take a derivative and evaluate at pi over 2, I could do it. It's a bit messy, right? But what I really care about is if I take x equals xe plus psi, I get psi dot dot is, let me just, like that. I'm just plugging it in. And as far as the behavior, okay, I'm going to, if I do an expansion just of that term, cosine of pi over 2 plus psi is cosine of pi over 2 is 0. Plus derivative is minus sine of pi over 2. So this is just minus sine pi over 2 psi plus things that look like psi squared or smaller. So that's minus psi. Plus dot dot dot. So I've kind of cooked this problem. I don't care about doing anything with this term because it's positive. Same kind of argument. I don't need to do anything with that term because it's positive. And that term is negative. So right away, without doing any f derivative calculation, that single expansion tells me that the psi looks like psi dot dot equals negative something times psi, which means psi is sines and cosines, which means it's stable. So this is positive, is greater than or equal to 0. That's positive. That's negative. Psi stable. Okay. Okay. Right, so want to take things up a notch a little bit and bring in a second variable. So coupled oscillations. And the main idea is that this argument that we've been making about stability, perturb, look at the behavior that works for systems of equations as well. To give a motivating example, let's imagine, where'd it go? Let's imagine the following system. I have a wall here, a wall over here, and I'm going to put 3 different springs in there and 2 different masses. I'm going to put a mass here, a mass here, spring, spring, spring. Okay? So I have 2 masses. Let's call each of them mass M, and 3 springs, and let's give each of the springs same rest length L and the constant K. Okay. Now let's suppose that the setup is like that. So this is a rest state. That's exactly L, L, L. Okay. So it's happy. All the springs are where they want to be. But then I do something. I pull one of the springs, or I move it. So I perturb the system. And now I'm going to let the dynamics take over. So how do I keep track of where the masses are? So if I kind of bring those rest lengths down as dashed lines, then at any given time, what I can do is keep track of this distance, which we'll call x of t, how much the first mass has moved from its rest spot, and I can keep track of this second mass by that distance, which we'll call y of t. Okay. Now I want to think about Newton's second law, and it looks quite complicated. It is a bit complicated, but if we take it sort of one mass at a time, so if that's mass 1 and that's mass 2, that's Newton's second law. So mass 1, it has a force. All the forces are just on that axis. It is 1D motion, but with 2 variables and sort of complicated interaction, right? So I'll call this force 1, which is the force of that spring on that mass, which is minus kx, which is to say if x is positive, the spring to the left of that mass pulls it back, sort of a minus. I have F2, so that's from spring 1, or maybe we can call that F. Call that F1. I have a force 2, which is the spring to the right of mass 1 is going to pull on it. That one's a little harder because it depends on the length of that second middle spring is y minus x. Right? So there's a k y minus x, and you have to think about the sign there. So if y is bigger than x, then that second middle spring has been stretched, which means the mass to the left of it is being pulled to the right. So that's a positive force. Okay. And on mass 2, I have force 3, which is the spring, the middle spring, now applying a force to the to mass 2. And actually Newton's third law, there's an equal and opposite. This is minus F2. That's minus k y minus x, which is to say that that spring, if it's stretched, is pulling that particle onto the right of it to the left. It looks the same as that one with a minus. And then F4, the final spring, pulls on the mass since y is the displacement there, that one ends up being like a k times y. But if y is positive, then that spring on the right, all the way on the right, is compressed, which means it's pushing to the left on that second mass, which means I need a minus here. Okay, so that you kind of have to keep your bearings to think about all the different forces on each of those springs, but they're all just the same spring law we've been looking at. And therefore, if I write that as a system, Newton's second law, I get m x dot dot is just the sum of the forces on that x, that mass 1, which is just F1 plus F2, which is, if I combine those two terms, I get minus 2 kx plus ky, and m y dot dot is F3 plus F4, and if you combine those two terms, you get kx minus 2 ky. Okay. So you could attempt to solve that system. It is doable. It's a linear equation, linear set of equations. What we really want to ask about is, there's a clear equilibrium where x equals y equals 0, and I want to ask about the stability of that equilibrium and sort of get a sense of the behavior. Let's pick that up on Thursday. Let's get going. So I've put the spring problem we introduced at the end up there, so we have it for reference. And I've given you another challenge problems. These are ones that aren't part of problem sheets, just fun exercises to think about. So the idea is you have a spring, you have a string, then another spring, and then a weight down here. Okay, just being pulled down, and it's fixed up at the top. And then I have two blue strings, one blue string going from that spring to the weight, and another blue string going from there to there, and they're loose. They're longer than this setup is right now. And I'm going to cut the red string so the whole thing stays attached. And the question is, does the mass move up or down? This is entirely within our material to understand and analyze, and actually the analysis the answer can vary. I'll give you that hint. I've taken this, if you guys know the YouTube channel Veritasium, there's a video, entire video on this concept. I don't want to tell you the name of the video because that'll give the answer away, but if you want to search for it, you can. My general idea was not to give out the answers to these at any point, because in some cases there's not a single answer. But you're welcome to come discuss with me. If anyone's thought about my rock-shaped leaf, I'd be happy to know what you're thinking. Okay, so leave that there. And before we think about the answer to that one, we're going to think about the question more generically. So let's come over here and talk about coupled oscillators. So the generic system is we consider two particles in 1D still, so we'll call it just x of t, y of t. Anyways, that's their positions. Such that are satisfying Newton's second law. Although we can think about this just generically, mathematically, it doesn't have to come from Newton's second law, but the equations we're thinking about are x double prime, x dot dot is, let's give it a generic f of xy. and y dot dot is some g of xy. So, of course, that's an example. Coupled simply means that the dynamics of x I can't understand on its own. It depends on where y is, and the dynamics of y depends on where x is. They're coupled together. Okay? There's lots you can do with that kind of system. We will play with these more generically in some other situations. What I want to do today is just ask the question about linear stability, extend what we were doing with 1D linear stability to this situation. And so we start with an equilibrium point. So XE, YE is an equilibrium point. If F and G are both 0 at that point. And now we're going to do the same conceptual thing. We start, so at that point nothing happens. There's no acceleration, which means if there's no velocity, the system just stays there. And so I want to perturb a little bit from that point and ask what that perturbation function looks like. So to address stability, we let x of t be xe plus a function which we'll call psi of t, and we'll let y of t be y sub e plus an eta of t. Again, assume that each of these functions is small in magnitude. And same idea, I want to then plug those expansions in to the governing equation, Taylor expand, and keep just the first terms that stay around. So plug in, expand. This is now a 2-variable Taylor series. So for instance, f of xe plus psi ye plus eta is f xe ye, which is 0 by construction, plus, looks like a regular Taylor series, but you need to take a derivative on the x times the x perturbation plus a derivative on the y. So you get a df dx at that xe ye times psi plus df dy at xe ye times the perturbation in y, which is the eta, plus more and more terms that are all smaller. So we tuck everything else into a dot, 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 and all that dot, dot, dot is quadratic or smaller. Right, so these are psi squared, eta squared, psi eta, or smaller, right? Actually, we don't get a psi eta. Okay. Which means that if I do the same thing for the G, I can collect this as a vector equation, which is going to look like psi dot dot eta dot dot, let's write that as a vector, is equal to a matrix M, which is composed of these partial derivatives evaluated at xe, ye, which we'll write in a minute, times the vector psi eta, where M is defined as df dx, df dy, dg dx, dg dy, evaluated at our equilibrium x, e, y, e. And if you just think about the first line of that, that's exactly what I get with this expansion here. Now, the nice way of writing it that way is this is constant. This is a matrix, but this is a constant, which means that as a vector differential equation, it looks like a very simple linear differential equation. Right? So this is called the linearized equations of motion. These are. And our question, as before, is if I solve that for given m, for given x, e, y, e, what kind of functions are psi and eta? Right? So the key, as I said, is that m is a constant matrix. Which means that the system looks like psi dot dot equals constant times psi, except instead of psi being a scalar, it's a vector, right? So, but with psi, a vector made up of the components psi and eta. So we know how to solve that, and if you think how you first learned how to solve that in A levels, say, we say, okay, well, the second derivative needs to give me back something close to the thing I started with, so let me look for an exponential solution, and then we look at these different cases. Right? So exact same thing works here. So what we can do is we can seek a solution where psi is some vector, call it A, times an exponential e to the lambda t. And so if A is, say, alpha beta, then that means that we're taking psi to be alpha e to the lambda t and eta to be beta e to the lambda t. Right, now what happens when I plug in that ansatz into this equation psi dot dot equals m times psi? Well, say take psi dot dot, I just get a lambda squared times the same thing back. So I get a lambda squared a e to the lambda t equals m times psi, but m times psi is just m a e to the lambda t. Which means that I can get rid of the exponential and I can factor out the a, and I get an equation m minus lambda squared times identity matrix times a equals 0. See that? In other words, it's an eigenvalue problem, which I think you guys just did perhaps last week, linear algebra. So that has solutions if the determinant of m minus lambda squared I is 0, which means that lambda squared needs to be an eigenvalue of the matrix M, and A is the eigenvector of M. solutions if determinants of m minus, lambda squared I equals 0. So lambda squared is an eigenvalue of m, and A is an eigenvec. Okay. So let's think about that determinant. So if I take a generic M, say A, B, C, D, so I don't keep having to write these partials of F and G. Let M be A, B, C, D, then determinants of M minus lambda squared I well, let's do it this way. If I work out that determinant, put a minus lambda squared on the A and the D, and I'm just going to do a little bit of one more algebraic step, which is just to factor things, then I get the equation lambda to the fourth minus A plus D lambda squared plus AD minus BC equals 0. In other words, I have a quadratic equation for lambda squared, which is not surprising because it's a lambda squared that's sitting in my determinant 2 by 2 matrix, which means that I can write lambda squared, let's write it lambda squared plus minus, as the solution of that, which is 1/2 A plus D plus or minus the square root of A plus D squared minus 4 AD minus BC. Okay. Fine. Now, what do I really want to know? So there are 2 roots there, but that's lambda squared. So each of those 2 roots, I take a square root with a plus or minus, I get 2 roots. So there's 4 lambdas here, right? And you can see they're potentially complex. And what I really want to know, think about where we started. I took a solution of an exponential, and that's the form of my perturbation, my psi and my eta. And I'm asking about stability, and stability is what kind of functions are those? And if they're exponentials with a positive exponential, then that's unstable, because that means the solution's going away from the equilibrium. So to be stable, it must be the case that I have no real exponents. For any, so I need all 4 of these lambdas to have, if they have a real part, it has to be negative, okay? So we have to be, now it's a complex analysis kind of question. I need to think about these roots and what are the possibilities. So let's write that down. So my notes, there are 2 roots for lambda squared, which implies 4 roots for lambda. The roots, the eigenvalues equivalently lie in, at least they certainly potentially lie in the complex plane. And if any of them has real parts, positive, then when I put that back in my exponential, that's unstable, right? The equilibrium point. And the corollary to that is that if all four of them have real parts less than or equal to 0, equilibrium is stable. Here. So if all four lambdas have non-negative real parts, non-positive real parts, the equilibrium point is stable. Okay. So let's think about what that means. So here's lambda squared is a plus minus. So if lambda is complex, I was going to say alpha plus minus beta, but we've already used those. That's all right. Okay, mild abuse of symbols I've already used above, but I'm barely going to use them here. If alpha is complex, it's going to be a complex conjugate, right? And that's, of course, coming down to that discriminant being negative. And, lambda squared is complex. It's going to be a complex conjugate. And the way to think about that is to write that as like a polar form. So that would be like an r e to the plus or minus I theta. And so if I were to draw that, in a real imaginary axis, that means I'm taking there's my theta, there's my r, there's my complex conjugate. So that's lambda squared. What is lambda? I take the square root of that, I get the square root of r, and I cut the angle in half, and I get a plus or minus. Right? And this is lambda plus minus. So lambda, there's four of them, as I said, is going to be plus minus root r e to the plus minus I theta over 2. So where are those roots living? In the square root. I'm chopping the angle in half, square rooting the radius, but I'm getting a plus minus. So those come to, say, here and here, but also here and here. So those are my lambdas. Yeah? The point is, because of that plus minus on the radius, the square root of the radius, two of those have whatever side whether the lambda squared was over here or over here, that square root has two of the roots living in the right half of the plane, which is where real part is positive, which is where things are unstable. So it looks like everything's ending up to have some positive exponents and unstable, unless, so this is always going to lead to an unstable equilibrium. So the only way to get stable is if that beta is in fact 0. So it's a bit more than that. If beta is 0 and the alpha is, if beta is 0, if beta is 0, then that means that this is positive. This square root is positive, which means my lambda squareds are both real, which means they're lying on the real axis. And if I take the square root of 2 lying on the real axis, it depends on whether the real thing was positive or negative, right? If the, let's try the picture again. If my lambdas are like, if that's my lambda squared, say they're both real positive, then of course take a square root. I'm keeping something that's real and positive. That's bad. Okay. If my lambda squareds are real and one's positive and one negative, same story, right? One of them is going to stay positive. The only scenario that works is if my lambda squareds are both negative and real, because when I take the square root of that, obviously we just think of it, square root of negative gives me an imaginary, or in this angle cutting in half thing, I end up with, for roots there, that's lambda squared, lambda goes here and here. Okay. So the only way to get stable equilibrium is if both lambda squareds are real and real and negative. So that all 4 lambda are purely imaginary. As a consequence of that, the system we're starting with, x double dot is f of xy, y double dot is g of xy, cannot have decaying oscillations as an equilibrium point. So my equilibrium points are either pure oscillation, right? Lambda is purely imaginary, or unstable. Either pure oscillation or unstable. In other words, we can't have Does anyone want to wager a guess physically to why decaying oscillations are not possible? In other words, I'm saying there will be no solution which is like an exponential with a negative real part times a sine and a cosine. That would be oscillation that's damping out. So that we can't have. I mean, you can have a term like that, but that's not the behavior, because you would also have an exponential with a positive multiplying a sine and a cosine, which is unstable. So that's what the mathematics says. Physically, if you think about maybe the picture over there, or the generic system over here, what is it about the system we've set up that makes this the case? Does anyone know? It's an energy argument. So when we're sort of thinking of simple springs, decaying oscillations comes when we add something like damping. And there are no x dots in our main equation, just x and x double dot, which means there's no damping which means there is an energy conservation. And I'll leave it, we'll do a bit with this in other contexts, but just to make a quick note here, if you define v of xy such that dv dx is that function f with a minus, and dv dy is minus g, then we have a two-dimensional, or not two-dimensional, two-variable energy conservation law, which looks like that. Okay, because I didn't put an m over there, there should be an m for the mass, and be kinetic energy plus a potential energy is constant. You can quickly check that. I won't do it on the board. Quickly check that just by taking a d dt across that equation, and then you'll get the sum of the two Newton's equations. So you'll get that the sum of the derivative of the left-hand side must be 0. And what that means is that we could, in principle, understand the motion by drawing not a one-dimensional, but a sort of two-dimensional energy landscape, v of xy, and the stability works the same way, that if that two-dimensional landscape looks like a valley, then the point at the bottom is going to be a stable equilibrium, and if it looks like a hill locally, then that equilibrium will be unstable. Okay, of course, the motion is more complicated because now the ball particle can move in more complex ways. But the same ideas work. Okay, so we can't have, so either we have pure oscillation or we have instability. Let's take that a little bit further. So I imagine I have 4 lambdas. And then we say each of those lambdas, each of those lambda squareds has an eigenvector, right? And then say in general, since it's a linear system, the solution is formed by adding up each of the component solutions, the linear superposition generically, I find a lambda, I find an alpha and beta, the corresponding eigenvector. I get a solution which looks like that. I'm going to have 4 of those. And my full solution is just the sum of those 4 because this equation there is linear equation. Okay. As a kind of a side note, there's a case that's slightly trickier to deal with, which is if I don't actually get 4 lambdas. And when do I not get 4 lambdas? If this square root comes out to be 0, I don't get 4 lambdas. I only get 2 lambdas, 2 lambda squareds. Or sorry, 1 lambda squared, 2 lambdas. This is the case of a repeated root. And I'm going to kind of leave this as a side note because I think we won't really do it. Repeated roots can be harder to deal with. But just to give you a context, if you think about the equation x dot dot minus 2x dot plus x equals 0, I solved that using standard techniques. My characteristic equation, I take x equals whatever a e to the lambda t, I get lambda minus 1 squared equals 0. That's this sort of one-dimensional repeated root case. Lambda equals 1 is the only root. And I think you guys know, or you've learned, maybe you don't have the rigorous derivation, but you've learned what you do in that case. And what you do in that case is one solution's like an e to the t, because lambda equals 1. And I get another solution by plopping a t in front. So the two solutions b t e to the t. I won't say really more about that. I think we won't worry about that case. The stabilities can be a bit harder to analyze when you have the two variables. Even where that t e to the t comes from, I think in second year differential equations course you'll explore that a bit more. So just an acknowledgement, for the most part, we will stick with this sort of case where all the lambdas come out, I think exclusively where the lambdas come out as non-repeated roots, in which case I take a sum of these four things and okay, so let's think about this case where if all 4 plus or minus lambda plus or minus are pure imaginary, so lambda is plus or minus I omega plus minus. So I have two different omegas and then get a plus or minus for the lambdas, my four roots. So each of those omegas being real and suppose positive, then those omegas are called the natural frequencies and what does my full solution look like? The general solution, we need to bring in the eigenvector. The eigenvector is associated to lambda squared, right? So lambda plus or minus squared, the eigenvalues are real. That's the case we're thinking about, which means that the eigenvectors are also real. Let's call it, say, alpha plus minus beta plus minus are also real, which means that one solution is say alpha plus beta plus times e to the lambda t, but lambda's complex. Oh, okay, we'll write it that way for now, is a e to the I omega plus t plus b e to the I omega plus, sorry, minus omega plus t. So I'm looking at one of these guys. The lambda squared was real and negative, which means the lambda was imaginary, and I'm calling that plus or minus I times omega. So I'm just taking the plus here, and I've got a plus or minus, which I put inside the exponential, and with some arbitrary constant, times the eigenvector associated with that lambda squared. And now it's just a game that you do anytime we're solving linear constant coefficient equation, which is I don't really want a complex solution. I want a real valued solution because it's a physical system. So I just turn that into sines and cosines and make a clever choice of the a and the b so that it ends up purely real. So that's the same as alpha plus beta plus. I can either write that as a sum of a sine and a cosine, or I can do this trick where I stick 1 degree of freedom as a phase shift. A plus cosine omega plus t plus call that phi plus. And what you're really doing here is choosing B to be a conjugate so that when I write those complex exponent and sines and cosines and I add them together, I get rid of the imaginary bit. And I just end up with a sine and a cosine, which I then take one more step and smush them together to be a single cosine with an arbitrary phase shift. Of course, you could leave this as a sine and a cosine of omega plus t. So that's one solution, and of course I can do the same thing for the lambda minus, the omega minus. And you see that the full solution is a combination of cosine of an omega plus t and a cosine of an omega minus t with a direction based on that eigenvector. Okay. So let's take these results back to that triple spring, but first I want to make one observation, which is that if we compare everything we've been doing today in this 2D setting to the 1D setting, you realize that though that's not the way we solved it in the 1D setting, the analogy is exactly the same. So if I'm in 1D, so x dot dot is f of x, I just want to see the direct parallel with what we've done here, where we get to this eigenvalue problem. Okay? So x dot dot is f of x, so I start by saying f of xe is 0 as an equilibrium point. I expand, step 2, x is xe plus psi of t. And that gives me an equation psi dot dot is f prime xe times psi. And rather than just solve that directly, let's do what we did over here, which is say, okay, let me look for an exponential solution. ae to the lambda t. And I can get the same step. So that's going to give me an a lambda squared e to the lambda t over here, and f dash xe times a e to the lambda t over there. So if I factor those in the same way we've done here, then I get what looks like a 1D eigenvalue problem, and indeed is, which is, let's write it this way, f dash xe minus lambda squared times a equals 0. Okay, so of course there's not really an eigenvector to this. It's any a is going to work, but nevertheless it has the same structure. And I need this thing to be 0, which defines my lambdas. And then I make the same argument that lambda squared, that lambda needs to have non-positive real part, stable if real part of lambda is less than or equal to 0. But lambda squared is just fxe, f prime xe, which means lambda is plus or minus the square root, which means the only possibility is what we've highlighted the other day, which is that I need f dash to be negative so that lambda is imaginary, right? Okay, so though we didn't think about it that way, it does have the same mathematical structure. And good, yes, so let's come back to this problem. Right, so here f is minus 2kx plus ky. G is kx minus 2ky. We start by equilibrium points. So I need those equations to simultaneously be 0. There's clearly a solution at x equals 0, y equals 0, which is how we've set it up, right? Those are the displacements from the rest lengths of the spring. So that's clearly an equilibrium point. Is that the only equilibrium point? You can look at that linear system and ask whether it has other solutions. If I write that as a matrix system, that's going to have a determinant that's non-zero. So the only solution is the 0, 0, 1. Which of course makes intuitive sense. Since those things are at their rest length, only when x and y are both 0, it wouldn't make sense for there to be an equilibrium at any other values. Okay, so if we want to analyze the stability of that equilibrium, we play this game that we've been doing over here. So the matrix M, we take the partials of f and g, x and y, evaluate at the equilibrium points. Actually, this one's automatic for us because this is already a linear equation, so we don't even need to do that. We just read off the the coefficients of f and g. So I get a minus 2k, k, k, and minus 2k. Not quite that, actually, if I want to follow what I've been doing, that little m sitting over on the left, the mass I didn't have over here, so I need to absorb that into my f and g. So this should really be a 1 over m. And of course, everything has a k, so I could have just factored that out as well. So it's k over m times minus 2, 1, 1, 2, and being repetitive, but that's our process. Psi dot dot eta dot dot is that m times psi eta, and determinant of m minus lambda squared I equals 0 gives us the equation lambda squared plus, sorry, this is a minus, so I put minus lambda squareds there and there, multiply together, the minuses go away, so it's lambda squared plus, not going to ignore the k, so plus 2k over m squared minus this guy, which is just a minus 1, but times k over m squared. K over m squared minus, why did I put k over m squared? My notes say squared, but now I'm thinking that, I don't know why that would be squared there. K over m. This should just be k over m, right? minus 2 minus k over m minus 1. I don't see why. Okay. Possible question there. So I can solve for my lambdas. Lambda squared is, do I need that? Okay. Okay, I think this is right. So you get lambda squared is k over m times minus 2 plus or minus 1. And that must be a squared then. Sure. In any case, I think the important thing is here, lambda squared has a minus 3 or a minus 1. So they're both negative, which means lambda is purely imaginary. All four lambda is purely imaginary, which means we have pure oscillation. Right? So lambda is plus or minus I times root k over m, and plus or minus I times root 3k over m. And the eigenvectors, if you do that calculation, you get 1, 1 associated with this first one, and 1 minus 1 associated with the second one, which means we'll end with the general solution, which would be xy, really psi eta, is 1, 1 times a cosine of root k over m t plus phi plus 1 minus 1 b cosine root 3k over m t plus, let's call it psi. There are 4 unknowns in that, arbitrary constants a, b, phi, and psi. And that's because I need to give initial conditions and initial velocities for x and y if I want to have a full solution. This shouldn't come as a surprise that I have these 3 springs lined up and the equilibrium is stable. I think what's a little bit surprising, a bit unexpected, is that the natural frequency of that system consists of 2 components. So there are 2 natural frequencies. There's root k over m, and that's not surprising at all because I have 3 springs, and each of those springs has a natural frequency root k over m. Right? That's how each spring individually would oscillate. What's interesting is that when you line them up like this, you get an extra mode of oscillation, which is root 3 times that. So the fact that you have 3 springs, you pick up this root 3, and so their oscillation is a combination of these 2. This system, of course, you can do lots of little variations on it and create, it's a rich system. I can change the rest lengths, I can make one spring stiffer than other springs, et cetera, et cetera. This is, I would say, the easiest version. Okay, good. Let's leave it there. Do give that, whether you want to solve it directly or not. I think there's some interesting concepts in this cutting the string problem that's connected to what we've been thinking about. Right, thank you.